First of all, let's talk about the actual idea of induction. What is the logic behind it? Because these are proof methods, so it's a very logical thing. Now, it's basically a series of statements, and then we link it together using what's called logical connectives. We have this statement. I've just called it S for statement. So statement N, that is what we want to prove. So it's some statement that has to be proved for every case. Statement, well, I've called it 1 here. It's not necessarily 1 every single time. Mind you, in extension 1, I think it always starts with 1. Extension 2, it might be something else. But basically, we're proving the statement is true for the very first case. Now, this is sometimes called the base case, so where it's starting from. Then we have an assumption. And then we basically assume what it is we're trying to prove. We just assume, yeah, okay, this is correct for just a general case. And we usually replace the pronumeral. The most common one is K. We see that a lot. Well, I'll replace the N with a K. This is going to be my general number that I'm substituting in. Then we go and prove that the next case is also true. Now, I've said K plus 1 because, again, that's the most common one. It doesn't necessarily have to be. If you're proving it for, say, even numbers, the next case would be K plus 2. And then we tie it all together. And these are what we call the logical connectives. Okay? So here's all the 4 things. So if I've got the S1, what I've called S1, and, so that symbol there is the logical connective, the symbol for and. So I have S1 and I've got my assumption. I've got those 2 things. This arrow is really important in logic. It's implied, also known as if-then. Basically, it's if-then statements. If I've got this, then I can say this. And that's the heart of any deductive proof. Back when you did geometry proofs, that's what you were doing. You had if-then statements. If I know all the sides are equal, then I can call it a rhombus. So if-then. So I've got these 2 things, then I can imply that the SK plus 1 is true. Whoops, come back. Imply the SK. Now, once I've done that, the final part then is to induce the final solution with another if-then statement where we say, hang on, if we've got all those conditions, then it must be true for every case. Because look at what we've just proven. We've got that it's true for the first case. And we're assuming it true for any general case. We've got these 2 things. If I've got those 2 things, I can imply it's true for the next case. So if I've proven it's true for the first case, then I can prove it's true for the next case. Well, if I've proven it's true for the first case, then it must be true for the second case. But now I know it's true for the second case. So I can imply it's true for the third case. Now I've got the third case. I can imply it's true for the fourth case. That is inducing a solution. Okay. So how do we structure the proof? The structure is key. Remember, when you are writing a proof down, remember, it's not for you. You're presenting it to someone. You're trying to convince them of your argument. It needs to make sense. So how do we structure it? Now, you don't actually write step 1 and step 2. I'm just saying these are the steps. Okay, we'll go and prove it's true for n equals 1, or whatever that first case is, that base case. So that I will do. Then, the second part I needed was the assumption. I want these 2 things. So, all right, I'll go and make the assumption that it's then true for n equals k. Most commonly, k will be a positive integer, but you have to define what this k is, and you match what it is in the question. So if it was even numbers, you say, well, where k is an even number, whatever. But you basically match it. You define what k is. So we've got those 2 things. Remember, we had to have and those. Going back to set notation or the language of logic, I could write that statement this way as well. Assume the result is true for n equals k, where k is an element of, remember that notation from set theory, is an element of the positive integers. Z was our symbol for integers, plus is saying I want the positive ones. Here is the deductive proof that lies inside the inductive proof. people don't often realise that an induction is an idea and it's a collection of several things. There actually is a proof within the proof. And this is the heart of an inductive proof, is the actual proof you use inside it. Now, of course, I'm doing it deductively. There are other methods of proof which you could also use in this step, but a deductive proof is by far the most common way of doing it. So we're going to prove it's true then for the next case. And we needed all these things to be able to induce a solution. And when you do prove it and you conclude your proof, I was saying it's an if-then, it's an imply. So you need to write that conclusion down that you've done that. Now you notice I've written it sort of backwards. I've actually said it's true for n equals k if it's true for n, but that's just grammar. I mean, it's the same thing. I'm saying if I know it's true for k, then I can say it's true for k plus 1. And some people prefer to write it that way. You know, if it's true for n equals k, then it's true for k plus 1. But remember, this is the heart of it. This is our if-then statement. Then the final bit is tying it all together. That inductive. So we induce the solution by linking everything together. We say, well, hang on, I've proven it's true for 1, and I've also just proven that it's true for k plus 1. If it's true for k, well, I know it's true for 1, therefore it must be true for 1 plus 1. And so you don't have to write that all down. Well, if it's true for 1, then it's true for 1 plus 1. And if it's true for 2, it's true for 2. You just basically say, well, look, I know it's true for 1. I went and proved that. So then the result is true for all possible integral values. But that very last few words is so important, because how can you make this claim? Well, we say, well, by induction. I'm inducing it from all these other things that I've just done. Don't leave that off. That is important. And if I wanted to write that final statement using set notation, the language of logic, I would write it very similar. Since the result is true for n equals 1, but then I could write it like this. Then it is true that upside down A symbol means for all. So for all n, remember, it was n we were actually proving, not k. So for all n that belong to the positive integers. So n is an element of z plus. That's a logical way of writing that conclusion. And we'll, in extension 2, learn a lot more about the language of logic and the connectives we use and things like that. Okay, let's look at some. We have formulas for adding up arithmetic series. We have geometric ones. So 2 common number patterns. But obviously there's lots of other number patterns out there which we don't have formulas for. Well, we do, we just got to prove them. And that's what we're going to do here. We're going to prove this number pattern. If I add up the odd numbers squared, so 1 squared plus 3 squared plus 5 squared, the general term would be 2n minus 1 squared, then I'm claiming that this formula will be 1/3 n, 2n minus 1, 2n plus 1. That's my claim. That's what I'm going to try and prove. So, all right, notice I didn't write step 1, but I'm still explaining what I'm doing. Someone is reading my solution. All right, I'm going to prove it's true for the very first case. The very first case is when n equals 1. This is one of the rare times I will actually use left-hand side and right-hand side in a proof. Left-hand side, so on the left-hand side, the very first term is 1 squared, because I sub that into my general term, that's what I get, and that equals 1. Show the substitution. Don't just write left-hand side equals 1, show the substitution. We have to show that, hey, when we use the left-hand side, we get the answer 1. On the right-hand side, again, show the substitution in the formula. Oh, okay, and then I work it out, and I get 1. I can then make this conclusion, the left-hand side does equal the right-hand side, and that's why I use left-hand side and right-hand side for this one. So I can make that conclusion. Oh yes, well the left-hand side is equal to the right-hand side. This is true. Now that I've got the complete picture there, I can explain better why you don't just write down 1. Imagine this for a proof. Left-hand side equals 1. Right-hand side equals 1. Therefore, left-hand side equals right-hand side. That's not a very convincing proof. You say, that's 1 and that's 1. Oh, yeah, right. How'd you get it? Okay. Showing your proof. Showing how you get it. So hence, yes, it is true for n equals 1. I just tidy up that little piece of the proof. I've got that piece that I wanted. Remember, that's what I called, again, I wouldn't write this down, but that's what I called S1, the base case, the very first case. Okay, The next thing I wanted to do was make the assumption. So I'm going to assume the result is true for n equals k. And I'm using the set notation here where k belongs to the positive integers. Because I'm talking about a series here, and we have a first term, we have a second term, we have a third term, so n's got to be a positive number. But not only do I write that down, I write down what my assumption is. Someone is reading your proof, they need to know what your assumption is. They need to know what you're assuming. I'm assuming 1 squared plus 3 squared, but basically it's the same thing, but you'll notice I've just replaced n with k. 2k minus 1 squared equals a third k, 2k minus 1, 2k plus 1. That is my assumption. So now I'm going to prove it's true for the next case. But again, write down what you're trying to prove. If I'm reading your proof and you don't write down what you're trying to prove, how do I know you got there? You're just going to make some claim, oh look, proven. And I'm going to go, proven what? You never told me what you were trying to prove. How do I know you got what you were trying to prove if you never told me what you were trying to prove? So you write down what you are trying to prove. Okay. Now comes that key piece, the actual proof itself. And I'm going to use a direct proof here. For this sort of series one, I start off the same way. I will write out the series, the left-hand side if you like. But then I will rewrite it and write the second last term in. Now why do that? Because what it turns out is the second last term here I could call some k. And then all I'm really doing is adding the k plus 1th term. Now why is that significant? Well, go back and have a look at what your assumption was. And essentially in this type of proof for a series, you're assuming that the sum of the k, because you let n equal k, was true. I can get rid of all of these terms, this plus dot 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 and so on, and simply substitute in my assumption. Because I've assumed that all of that is 1/3 k, 2k minus 1, 2k plus 1. But now I've added this k plus 1th term. I've got some algebra I can play with now, and hopefully I can rearrange this and get the right hand side. Okay. Oh, yes. How can I make this claim? Explain myself. Well, that was by the assumption. I just used my assumption. Good. Someone is reading your proof. How do they know you got from there to there? They need to know. I got there by this using my assumption. Now, sometimes I suppose that's obvious, but sometimes in a proof you do something that's not obvious, and you definitely need to explain what you just did. Okay. You'll notice I did not expand the whole thing. That would be an incredible waste of time, because always keep an eye on what you're trying to prove. And you'll notice what we're trying to prove has a common factor of 2k plus 1. So why expand this all out only to refactorize it back in? If I see that common factor there, I'll take it out straight away. So both had 2k plus 1. What I'm trying to prove had a factor of 2k plus 1. I take it out. So what am I left with inside? I've got a third k, 2k minus 1 plus 2k plus 1. Again, look at what we're trying to prove. We actually do have another one of those factors there. It's not as obvious. But these two things have a common factor. And that common factor is 1/3. You see, this second term here is 1/3 times 3. So I can pull out a third because I need that in my answer. I pull it out, but when I pull it out, this second term now becomes 3 times 2k plus 1. All right, let's now focus on inside those square brackets. Expand out, it's a quadratic. Oh, well, factorising quadratics. What would that be? Amazingly, it turns into k plus 1, 2k plus 3, which is what we want. Excellent. So now I can make the statement. Well, yes, it's true. But remember, it's only true if that assumption that I substituted in was true. If that assumption's wrong, then this proof is a piece of garbage. Because if that's not true, I can't substitute that in for that. So that's why we need that if-then statements. I have proven this is true if it's true for k. So this only holds up if it's true for k. If it's not true for k, then this proof is a piece of garbage. But fortunately, we know it's true for 1, and that's where that last piece now comes in. We now go and induce the proof. Oh, there you go. Just pointing that out, that what I've basically done there, I've said, if I've got some k, I can imply some k plus 1. Okay, so the final one, now I can say, well, hang on, I know it's true for 1. We proved that. So therefore, logically, it has to be true for all of the positive integers. I can now induce it, because we said, look, if it's true for k, then it's true for k plus 1. I know it's true for 1, therefore it's got to be true for 2. Now I know it's true for 2, it's got to be true for 3. Now I know it's 3, got to be true for 4, and so on, and so on, and so on. And you can induce every possible positive integer. Okay. Ooh, oh yes, so that last bit, so there's that SN, that final statement that I want to write down. Okay, let's look at another one, but this time you'll notice on the left hand side, instead of writing it out with a plus, 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 dot, 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 it's in sigma notation, sum notation. Okay, we can do that. So this is the one we're trying to claim. Now, if we add up these things, or the sum, we get n on 2n plus 1. I personally like to rewrite it to get a feel for what actually is this pattern. But you'll notice when I rewrote it, I still kept it as the 2 factors on the bottom there. So the first fraction will be 1 times 3 in the denominator. The second one will be 3 times 5. Next one's 5 times 7. I can now sort of see what's happening here. This pattern is a fraction where the denominator is consecutive odd numbers multiplied together. So 1 times 3, then 3 times 5, 5 times 7. The general term, which would be that one up there, is 1 on 2n minus 1, 2n plus 1, claiming that all of those will simply add up to be n on 2n plus 1. This is our claim. Okay, let's prove it true for the first case. If I substitute in 1 on the left-hand side, I end up getting a third. Okay, what happens when we sub it into the right-hand side? 1 on 2 plus 1, yes, that's a third as well. Excellent. It's true for the very first case. I can make that claim. Brilliant. I've got one of the things I need. Let's make our assumption. I'm not going to assume it's actually true for every integer. No. N equals k, where k is some positive integer. I'll make that assumption. And I'll just write down what it is I'm assuming. That is what I'm assuming. Okay. I want to prove it true for the next case. I want to prove it true for k plus 1. Let's create the proof. So everywhere I see n in that formula they gave me, I'm replacing with k plus 1. And this is what I get. Let's do the proof. Again, series type. There it is, but then I've rewritten it with the second last term in there because, have a look at what we got. There is our assumption. So I can now just substitute in for my assumption. And again, I'm explaining how I did it. Yep, I've made this statement by assumption. Using my assumption, I can, if my assumption is true, then this proof will be good. If it's not true, piece of garbage. Okay. Keep an eye on what you're trying to prove. It's all one fraction. So let's combine this into one fraction. The common denominator would be 2k plus 1, 2k plus 3, which means in the first fraction the k has to be multiplied by the 2k plus 3. The second one, the denominator is okay, so it's just plus 1. We're trying to get the k plus 1. Okay. Oh, on the top there's a quadratic. Going to factorise. By the way, assuming you've substituted in everything correctly, you can save yourself a lot of time because logically you know where you need to go to. So there's no prizes in guessing what this is going to factorise to be. If you have a look at what you've got at the moment and where we need to go to, it looks like that this is going to have to factorise to be 2k plus 1k plus 1 so that the 2k plus 1s cancel. So there it is. Bang, it's factorised. So you can use that to help you do the factorisation. You go, hang on, logically, k plus 1 has to be a factor here, otherwise this isn't going to work. So there it is. Now the 2k plus 1s will cancel. K plus 1 on 2k plus 3, that is what we were looking for. So yes, the result is true for k plus 1, but only if that assumption we made is good. Only if it's true for n equals k. Not true, piece of garbage. Tie it all together. Well, hang on, I know it's true for the very first case, then it's got to be true for everything by induction. That's the method I have used to tie it all together. I've induced the solution. Okay, remember, 3 key parts to our proof. 3 key parts. setting it up. Prove it true for the first case. Assume what you're trying to do is true. State what you're trying to prove. Now, by the way, you don't have to do the first case first. Remember, because they're just two separate things. You just need both of them. Some people, it's very, very rare, some people do the second and the third bit first and then go, righto, well, I've proved it's true for k plus 1 if it's true for k, so now I'll go and prove it's true for the first case. That's perfectly fine. You just need those two things to tie together so you can make the leap. Okay, because then comes the proof. Remember, it is a deductive proof. So you provide an explanation, certainly for non-obvious steps, just like you would have in geometry. Vertically opposite angles are equal, whatever. Make it clear. And then you conclude that proof with the if-then statement. That's the type of proof we're doing here. If-then. And then we tie it all together with that conclusion. Now, I'm going to induce a solution. That's what I'm doing. Okay. 2A. We have some induction questions to try.